Hi everyone. Today we are going to talk about a very interesting problem in algorithms that is called the graph coloring problem. And the idea of this problem has to do with the following. When we talk about graph coloring, we are referring to the problem of painting or coloring the vertices of a graph, but in a way that no two adjacent vertices on the graph share the same color. And the idea comes, as the name may suggest, from coloring a map. If we have a map, and of course we would not like to use the same color to paint two regions which are having a common border. In order to distinguish between them, we will need to use different colors. But as you may also imagine, we are interested in finding the minimum amount of colors that we need to use in order to paint a map or a graph, so that we can distinguish every region with a different color or every vertex with a different color. And there are many applications of this problem. One of them is in scheduling. So let's suppose that we are generating the exam schedule for the whole campus. But of course, we will need to check things like there are students which are in different courses, and we don't want to program two different exams at the same time if there are students common between these two classes. So the way to represent this problem is using a vertex for every subject and an edge between two of these vertices if there is a common student between the two courses. And then we apply some techniques on graph coloring. We determine something that we call the chromatic number of the graph, and then that will give us information on how many slots of time we will need in order to allocate properly the exams. We will see the definition in more detail of the chromatic number in a moment. But there are there are other applications too, like in wireless communications. If we have devices which are adjacent, we don't want them to use the same frequency, otherwise they will interfere. But we don't have an infinite number of frequencies. So how can we manage the available frequencies so that we assign them properly? And again, this magic word of the chromatic number is gonna give us the information on the minimum number of frequencies that we may require in order to avoid interference. There are some other applications, some like in games that we play commonly, like Sudoku. And in this case, what we are going to do is to use a vertex for every cell of the Sudoku, and we will connect those vertices by an edge if they are in the same row or the same column or the same block. And then we can apply graph coloring, a modification of graph coloring algorithms in order to solve the Sudoku. So multiple applications for this problem, but let's go into more detail about what we mean by these coloring things. And there is an interesting theorem called the four-color map, which basically states that if we have a two-dimensional map with regions which are adjacent and some others are not, then we can paint this map by using four colors at the most. And by adjacent regions, we mean those which are sharing a common border, which is not just a point, it's a segment. And we can illustrate this with the map of the United States. And we can see that it is possible to use 4 colors in order to paint all of the states without getting confused. And we cannot do it with less than 4. We don't need more than 4. Of course, we could use 1 color for every state, but that would be a waste of colors, right? So we don't want to do that. Another concept that is going to be important is the dual graph. And this is because at the end, we were talking a moment ago about a plane with regions, and we want to translate the same information that is on the plane to a graph. So this abstraction is going to be done in the following way. We represent every region on the map by a vertex on my graph. The edges are going to be connecting vertices if the regions that are represented have a common border. And of course, again, we will consider that common border means a segment and not just one point. And what we obtain by doing this is what is called the dual graph of the map. So for instance, let's suppose that we have region splitted in the following way. And by doing what I mentioned before, we can build a map by getting one vertex for each one of these regions. So we have A, B, C, D, F, and G vertices, and then we can establish connections. So we can see, for instance, that there is a border between B and C. There is a border between A and C. So you can see, we can see C and D, D and E, D and E, and so on. So basically what we can do is that we can generate a corresponding dual graph that looks like in the following image. Of course, there could be some other variations of it, but at the end, the topology of this graph is going to be the same in order to represent the regions that we have up. And if we had this other map, then that would translate again into a dual graph like the one that we are showing. So we basically can check in this one, which is smaller, that for instance, in my graph, I have a connection between B and C, and that is because there is a common border between C and D. The same happens between A and B, between B and E, and so on. So this is basically the concept of a dual graph. So once we have this graph, what we want to do is to assign to each one of the vertices of my graph one color, but we don't want to have the case that 2 adjacent vertices are assigned with the same color, are painted with the same color. And then we have finally the definition of this marvelous concept of the chromatic number of the graph. This is going to be the least number of colors needed in order to color the graph, to paint the graph. So if we're talking, for instance, of a bipartite graph, that is a graph that has a certain number of vertices connected between them, and there is another set that is connected between them, and then the number of colors here is going to be something important, and basically the answer is going to be 2. We will see that in a moment. Now, this theorem is very interesting because long time ago, 1850s, somebody conjectured that the chromatic number of a planar graph is not greater than 4. And we will see the definition of a planar graph in a moment. We haven't defined it yet. But look, this conjecture was proven almost 100 years after. It was finally proved by two American mathematicians, Kenneth Appel and Wolfgang Haken in 1976. And this is actually the first mathematical theorem that has been proven with the help of computers. That is awesome, because usually before that, mathematicians were working alone using their brain and a piece of paper and a pencil. But these guys used theorem provers, automatic theorem provers. Although, particularly in this case, what they determined is that if the theorem was false, then there should be, of course, a counterexample, some planar graph that has a chromatic number bigger than 4. So they designed the structures that a planar graph may have, and they discovered that there were about 2,000 different types of structures, and they used the computer in order to check all of them to see if one of them at least shown a bigger chromatic number than 4, and they didn't found it. So at the end, since that was or those were the only possibilities of showing counterexamples, they demonstrated that the theorem was true actually, and this is important. Now, we were using the concept of planar graphs, but what is a planar graph? And basically what we mean by that is that when we have a connected graph, and this graph can be somehow drawn without any edges crossing in the plane, of course, then it is called a planar graph. And if it is possible to do this, then basically what happens is that the graph is gonna divide the plane into some regions that are called faces. So let's see an example. And something important to mention, that's right, something important to mention is that sometimes we draw the graphs in a way that edges are crossing, and we may think that for that reason they are not planar, but sometimes we can rearrange the drawing respecting the topology of the graph. And if we can arrive to an arrangement where these edges are not crossing, then it was a planar graph. So we have to be careful with that. For instance, in this case, if we look at this graph, we can see several edges crossing, the one that goes from 2 to 3, and the one going from 1 to 5, for instance, they are crossing, and there are many others. So if we just look at the image, we may say this is definitely not a graph, a planar graph. So, however, we can rearrange the way in which we draw, just the way we draw it. We retain all the connections in the way they are. If you check the one that is below, all the connections, all the edges are maintained. It's just that we put the points or the vertices in different places on the plane, and we can see that we can draw it in a way that no edges crosses. So this graph is definitely a planar graph. So we have to be careful with that. And what I was mentioning is that once we have a planar graph, we can divide the regions on the plane in phases. So for instance, this graph that we just showed has 3 different phases. One of them, of course, is here inside, the other one is this one, and the rest is 3. And the number of phases is not going to change no matter how we draw the graph, as long, of course, as we keep the edges without crossing. So at the end, we can also consider that the number of faces of a planar graph is part of the properties of the graph. And then we can, of course, be careful again when having something like that. So we can only count faces when the graph is drawn in a planar way. Of course, we consider these two representations of the same graph, we are going to get different number of faces. In this case, we may decompose it. So different numbers. It's the same graph. But the one that is valid is this one, because this is planar, or the representation, the drawing of the graph is the correct one. Now, this also is related with mathematics, are so amazing and I don't know. So there is a connection between the number of vertices, the number of edges, and the number of faces in any connected planar graph. And this relationship was established by Euler and is called the Euler's formula for planar graphs. Basically, this formula is very simple. It says that for any connected planar graph with B vertices, E edges, and F faces, we have this equation holding. The number of vertices minus the number of edges plus the number of faces is going to be 2 always for any connected planar graph. So we can apply this property for many other things. And there is another implication of planar graphs and coloring that is very important for computer science, and is to determine when we create what is called the bipartite graphs, partitions of sets at the end. Remember that the graphs are just the representation of relations between sets. But we are going to have one bipartite graph if the vertices of such graph can be split, can be divided into two subsets, A and B. And none of the vertices contained in A are connected. There is no edges between them. And the same happens with the vertices that are contained in B. But there are connections, or there could be connections, of course, between nodes which are in A and nodes which are in B. So when we have not just that, but a complete bipartite graph, we give them a special name using the K letter and two indices to represent the number of, or the cardinality of elements on one set and the other set. So if we see something like KMN, it means that this is a bipartite graph with M elements in one of the sets and N elements on the other set. So for instance, in this image here, we say that we have K2, 3, because clearly we have one set with 2 elements, and then we have another set with 3 elements. There is no connections. There are no connections between the elements in A. There are no connections between the elements in B. So it is a complete, because they are all connected against all, except of course between the same, in the same set. So this is a complete bipartite graph. And same happens here. So in this case, we have K33, because we have 3 elements in one and 3 elements in the other. All the elements on A are connected with all the elements in B, and so on, but they are not connected in the same set. So this is just notation, and it's very important because in many problems, we may see something like this appearing, and then we know, oh, I have a graph like this one. I know that it will have a connection with coloring of graphs. We will see. So the question that we are interested in answering when considering coloring of graphs is basically the following. What is the chromatic number of the graph? In this case, shown here, right? But in general, we want to, given a graph, answer if what is the number of what is the chromatic number of the graph? And in order to do that, we basically can look at the graph that we are showing here, and we know that at least I will need 3 different colors. Why? Well, because if I paint this with color 1, then I cannot use the same color for B, and I cannot use the same color for C because they are connected. So I will necessarily use a different color here, color 2, and I cannot use color 1 nor color 2 for C because they are all connected. So necessarily I will have to use a third color here. And this means that at least I need 3, maybe more, okay? And actually, for this problem, we can try to use the 3 colors that I mentioned at the beginning, and then we will notice that it is possible for this graph to use only 3 colors to paint all the vertices, having holding this property that no same color is used if 2 vertices are adjacent. So nice, right? So it means that the chromatic number of that graph is 3. So what is the chromatic number for each one of the following graphs? So let's suppose that I start assigning colors. I will write them instead of painting. So white, then I need to use a different one. Let's suppose yellow. But then, of course, I could use blue for the next one, but not necessarily because I could reuse the white, I'm sorry, because this third node is not connected with the first one. So perfectly, I can do something like this, and I am respecting the constraint that I had, and I can keep doing this all the way until I finish with all the nodes. So for this graph that we are showing, the chromatic number is going to be 2. I can paint this graph with only 2 colors. I cannot use less, and I don't need to use more. What about the figure that is on the right? Well, I can do the same idea. So I start with white, and then I use yellow, and then white, and then yellow. Oops. But now, for the last one, I cannot use yellow because I just use it and they are connected, but I cannot use white either because it is connected with the first one. So I will necessarily have to use another one. Maybe green, blue, whatever, different one. So it means that the minimum number of colors that I need to paint this graph is going to be 3, or that the chromatic number of this graph is 3. And the thing is, talking about the complexity of the algorithms to find this chromatic number, they grow with exponential cost in the number of vertices of the graph. Even finding an approximation to the chromatic number of the graph is going to be difficult. And that explains why scheduling final exams, for instance, is so difficult. How can we generate the list of the schedules for all the exams on campus, so to guarantee that no student has an overlap between them? We don't have this anymore, I think, with Tech 21, but we use to have that before, and it was a nightmare. And it may happen that at the end there were students with two different exams programmed at the same time, and we had to solve it somehow. But in general, most of them were not the case. So the thing is, how can we solve this problem in a systematic way? Well, we can use different alternatives, and one of them is to use a greedy algorithm. And the greedy algorithm is going to be very simple. Of course, we must be careful that this algorithm is not going to guarantee that we use the minimum number of colors. However, it will guarantee that we will get a upper bound on the number of colors. So whatever it says, it might be the maximum I could use. So that will give us some range maybe to consider. So basically, what happens is that this basic algorithm is never going to use more than the D colors plus 1, where D is going to be the maximum degree on the vertices in the graph. So if we have 5 vertices on the graph, my algorithm will never use more than 6 colors. Well, at least that is a bound, upper bound that we can consider. So let's look at this algorithm. It's very simple, as most of the greedy algorithms are. So the first step is to color the first vertex in my graph with the first color I have in my box of colors. Right? Then my second step would be I will need to consider the remaining vertices that haven't painted, and one by one, of course. And what I will do is I will color the vertex that I am analyzing now with the lowest numbered color that has not been used to color any of the adjacent vertices. So I have a box full of colors, but I won't go into the next one if I can use one before, respecting, of course, this property of no same color for 2 adjacent vertices. Of course, if it happens that when I am considering this color, I discover that it was used in an adjacent node, I cannot use it, and then I have to move to the next least number color. We will see it in an example in a moment. And of course, if at some point all the colors have been used, then I will need to incorporate another one from the box. Let's try to see how this works. So let's suppose that we have this graph. And what we are saying is that I will start with one of the vertices of the graph. Let's suppose that I do it with A. And then I say, well, I will use color 1 in order to paint this one. Then I will move to the following vertex, whatever. Okay, so maybe B. I cannot use C1 because B is adjacent to A. So necessarily, I will need to incorporate another one. So I go to the box of colors, and then I take the second color. And then I move to C. In C, I will start again from the beginning, if possible. So in C, I will check if I can use color 1. And then I notice that C and A are not connected. So definitely, I can use color 1 to paint C. Then I move to D. D, again, I will try C1, but C1 is used for C, for node C, and C is connected with D, so I cannot use C1. And then I try C2, and I notice that C2 is possible because the only other node that I have used that color is B, and B is not connected with D. Oh, so C2. And this process is going to repeat for all the vertices. So I move to E. In the case of E, I again consider C1, and I see that C1 is used in A and in C, but none of those vertices are connected with E. So I definitely can use C1. Then I move to F, which is the last vertex of my graph. And I can see that I cannot use C1 because C1 is used in A, in E, and in C, which are all connected with F. And then I consider C2, and then I notice that C2 is used in B and D, but F does not have any connection with C, with B, and with D. So I can certainly use C2. So the chromatic number of this graph is going to be 2. And we can see here the same thing that I did, but in a nicer way, cleaner way. And this algorithm, I can apply it, of course, for different problems. Here, I can do it. This is a representation actually using using real colors and not just the names of C1 and C2 and so on. What about this other case? Basically, it's going to happen the same. I mean, I will apply the same algorithm. It's just that in this case, we have more connections, but let's try at least part of the problem. So I start here, I use color 1. When I move, for instance, to B, I know that I cannot use C1, so I will use C2. Then I move to C. I consider C1. C1 is not possible because it is connected to A, but it is possible with C2 because C is not connected with B. So C2. Then I move to D. I cannot use I cannot use C1 because D is connected with A. I cannot use C2 because D is connected with B. So I will need to use a third color. So I go to my box and I take a third color here. Then I move to E. E is connected with A, so I cannot use C1. E is connected with C2, so with C, I'm sorry, so I cannot use color 2. But what about C3? Well, it happens that E is not connected with D. So I can use C3 here. And lastly, we go to F. In F, I try C1. And I see that F is not connected with A, that is the only vertex with the color 1. So I can use C1 here. So that means that here the chromatic number is going to be 3. And that's exactly what we are saying here. So pretty simple, right? The algorithm is nice, it's fast, and you can do more examples if you want to check even more. So the complexity of this algorithm, this greedy algorithm, is going to be V squared plus the number of edges in the worst case. So it's not that bad, quadratic. However, in the number of vertices. However, it cannot guarantee that it will give us the minimum number always. Sometimes the chromatic number that this, or the approximation of the chromatic number that this algorithm is going to give us will depend on the order in which the vertices are processed. And that is bad, okay? Because we cannot know in advance. For instance, let's consider these two examples. If you see, they are almost the same, except that the third and the fourth nodes are exchanged or swapped here and then in the other. And if we consider only these, these things, we can, for the left graph, we can color the graph by using only 2 colors. Moving from 1, 2, 3, 1, I'm sorry, 0, 1, 2, 3, and 4. And by doing exactly the same order, but in the right graph, we are going to need 3 colors. Let me see if I have the answer here. Otherwise, no. So we can do it. Color 1, color 2, color 2, color 1, color 2, right? So in this case, we have 2 colors. What about this one? Color 1, color 2, color 2, color 1, and then color, I'm sorry, oops, I don't think that I have, I don't know how to erase, oops, sorry. Okay, well, I made a mistake because the order, we are considering the order. So after assigning for number 2, we go to number 3, and number 3 can use color 1. And then when we want to color the node 4, we check that it is not possible to use color 1 because it is in 3. We cannot use color 2 because it is in 1 and 2. So we necessarily have to incorporate a third color. So here we need 3 colors. And it's almost the same graph. It's just that the order in which we are considering the graphs is slightly different. So we can see that the order affects our assignment. So let's see another example where we may notice what happens when we have a different order to visit the vertices of the node. And let's consider this graph. What we have on the left is basically the same thing as what we have on the right. It's just the order of the vertices have been, they have been labeled in a different order. So let's solve using the same algorithm that we were using, the one on the left. So if I start node 1, I can use, of course, color 1 here. And then I move to the second node. And since it is not connected with the first one, I can also use color 1. Then I move to the third node. It is not connected with 2 or with 1. So again, color 1. And the same is going to happen here with the fourth node. I can use the first color. Then I move to node 5. And I can try to use C1, but C1, I mean, node 5 is connected with node 2, with node 3, and with node 4, all of which have color 1. So I cannot use color 1. I will have to use color 2. Then I move to 6. 6 is connected with 1, with 3, and with 4. All of them are colored with color 1, but not with color 2. And color 2 is used by 5, but 6 and 5 have no connection, so color 2. And same exactly is going to happen with this node and with this node. So basically, we need 2 colors. The chromatic number for this graph apparently is 2 according to our algorithm. Now, let's move to the one on the right. Again, I will start in node 1, so I will use color 1. And I move to the node 2. Node 2 is not connected with node 1, so I can use color 1 again. Then I move to node 3. When I move there, I can try to use color 1, but since 3 is connected with 2, I cannot use that color. So I will have to use color 2. Then I move to 4. 4 is connected with 1, so I cannot use color 1. And it is not connected with 3, so I can use color 2. Then I move, oh, I'm sorry, I have a mistake here. But it's simple, 1, 2, 3, 4. This is 5. And this is 6, 7, and 9. Okay, so then I move to the vertex number 5, and I want to use C1, but this node is connected with the node 2, which is using color 1, so I cannot use color 1. Then I consider color 2, but 5 is connected with 4, which is colored with color 2. So I cannot use color 2, so necessarily I will have to pick another color from my box and use it here. Then I move to 6. In 6, I cannot use C1 because 6 is connected with 1. I cannot use C2 because 6 is connected with 3. But I can use 3 because 6 is not connected with 5. So C3. Then I move to 7. 7 is connected with C1, with 2, I'm sorry, not 2. So I cannot use C1. 7 is connected with 4, so I cannot use C2. And 7 is connected with 6, so I cannot use C3. So I will have to pick another color. Here it's going to be 4, and the same thing is going to happen with node 8. So I will have to use 4 colors. So you see, very likely the solution on the left is the correct one. That would be the chromatic number of the graph. However, my algorithm is giving a different answer for the same graph. And in the second case, it is telling me that it would be 4. So we have to be careful with that. And this is exactly with colors what we were showing. In the first case, we have 2 colors only, and in the second, we have 4 different colors. Now, there is another algorithm that we can use beyond the greedy one, and then this is called the Welsh-Powell algorithm. It was introduced in 1967, I'm sorry. And it basically introduced by trying to generate an upper bound to the chromatic number of a graph. So Welsh-Powell is also a greedy algorithm that will run on a static graph. The vertices, but in this case, the vertices are going to be ordered according to their degrees. So the resulting colors will be at maximum, the minimum between the number of the degree of the node +1 and I, where I is the number of vertices. So then what we are going to do is the following. This heuristic of ordering or considering the things using the degree of the vertices is called the Welsh-Powell algorithm. So let's see the pseudocode of this algorithm. It basically says that the first step is to find or to compute the degree for each vertex on the graph. Then we are going to list the vertices in order of descending degrees. We will start with the first vertex using color 1, and we will move down the list and we color all the vertices which are not connected to the one that I have colored with the same color. And I will repeat this 4th step to all the uncolored vertices with a new color, of course, in descending order of degrees until all the vertices are colored. So let's see how this algorithm works in practice. Let's suppose that we have this graph. The number, we have the labels of the nodes, and we have a number in parentheses here. The number is actually the degree of the vertices. So we have a 2 here, this one, because we can see two connections. We have a 4 here because we have 1, 2, 3, 4, and so on. Here, C has 5 connections, 1, 2, 3, 4, 5. All right. So that is basically what we have. So our algorithm says compute the degrees. I have done that. We have it represented on the graph. And then in this next step, we are going to start with the node that has the highest value. We are ordering them in descending order. So if I write down the list, it would be C with 5. Then it would be E with 4. Then it would be F with 3. Then B with 2. G with 2. A with 1. And D with 1. So I hope I didn't forget any. So we will start with the first one. And then I will use a color to paint this node. And I will also check all the other nodes which are not connected with this one, and I will use the same color. So the only one here that is not connected to C is G. So this is the only one that I can color with the same color than C. So this guy is gone. So now we are going to pick another color, and I will choose E, which is the second in the list. So I will color E with this color and all the nodes which are not connected with E. And the only ones that are not connected with E are A and D, right? So this guy is gone. Now we move in our list to the next element, which is F. F is going to be colored with this one. And there is only another node that is not connected with F that is going to use the same color. So at the end, what we are saying is that we will use 1, 2, 3 colors. And this is the illustration of how Welsh Powell works. Let's see. This is the solution. And we can apply it in another example like this one. So we can compute the values. So A has 1, 2, 3, 4. B has 3. C has 3, it's degree. D has 3. E has 4. Then F has 3. Then G has 4. So if I generate my list, I will have several with 4, A, G, and E. And I will have several with 3, F, D, C, and B. And that's it, right? So I will start with A, and I will use a color for that. let me use this one. So A is here. I will use this color. And all the nodes which are not connected to A, so we can basically use the same color here and there. And that's it. All the rest of the vertices have connection to A, correct? So we move to the next on the list, which is G. Oh, and let's see. Then we go to G and use this color. And all the nodes which are not connected with G can use the same color. And that is the case of B and only B. Then we go to, see, we go to E. E is gonna be colored with this one. And we don't have any other node which is not connected to E. So we will have to change our marker. And then this will be the last one. So basically we have used 4 colors. Or as the British may say, 4 colors. Is that right? Colors. I don't know. Okay, so you can apply then again for another one to practice, and the complexity of this algorithm is going to be quadratic, and that's it. So I hope you enjoyed learning a little bit about graph coloring and that you can apply it in an interesting problem. And that's it for today. See you.